In my previous lecture, I derived the following two equations. These are the kinematics equations for one-dimensional motion for constant acceleration. If you know three things about an object, that is, its initial position x naught, its initial velocity v naught, and its constant acceleration a, then at any time in the future you can calculate two things. You can calculate the position of the object as a function of time, and also the velocity of the object as a function of time. Now, hopefully in the last lecture, you were able to algebraically follow along with me as I derived these equations. But of course, as of yet, you really have no understanding as to what these equations really mean. You understand what these equations are saying by using them, and that's what we'll do here with a couple of examples. Before I begin these examples, however, I also want to lay out for you formally the mathematical procedure that you run through whenever you sit down and you solve a physics problem. To some extent, I've already been using this procedure over the course of the year thus far. However, let me lay it out formally for you here. What you will then see me do for the remainder of this course is you will see me employ this method, this recipe, if you will, over and over. So let me briefly run through the basic steps that you use when setting up and solving a physics problem. Okay, the first thing that you always do is you draw a diagram. You draw a simple diagram when applicable to the situation. Okay, secondly, you write down the known quantities. In other words, invariably in a problem, there are always going to be some known quantities that are given. You identify them and write them down. And then the next thing that you do is you identify and you write down the unknown quantities. Usually, at least in part, it's what's being asked for in the problem. So we write down the unknowns. And then afterwards, you write down the relevant equations that are applicable to the situation. You'll see me do that with these two expressions here. So write down the relevant equations. And if you've gotten to this step correctly in a problem, this right here is basically 90% of the game. Because usually then what remains is whatever mathematical manipulation you then have to perform in order to solve for whatever it is that you're looking for. Always break up the math. This is where the mathematical steps come in. Always break up the math into two parts. The first thing that you want to do is you want to simplify your equations as far as you can. You do so by plugging in your zeros. That is, whatever quantities are given as a zero, you immediately plug them into the equations themselves. So step 5 is plug in the zeros. This then simplifies the equations. And then after that, you perform whatever algebraic manipulation that is necessary to solve for whatever it is that you're looking for. So now let me go ahead and apply this method here to our first example for today's lecture. Go ahead and write it down briefly in your notes while I read it to you here. Okay, so a rocket accelerates at a constant 9.8 meters per second squared after starting from rest. In part A of the problem, how much time, in terms of days, is necessary for the rocket to reach a speed of 3 times 10 to the 7th meters per second? That speed is 1/10 the speed of light. The speed of light is 3 times 10 to the 8th meters per second, is one of nature's fundamental constants. That particular constant will become very important in this course later on during the second semester. Okay, so let's go ahead and immediately start to employ this method here when approaching this problem. Let me go ahead and do some erasing here first. Okay, so the first thing to do is draw a diagram. So let's say that the rocket begins here, like so, and at the end of the problem, it ends up over here. Simple as that. And now at this point, we start to write down the known quantities. A number of things are known in the problem. First of all, even though it doesn't explicitly say so, let's just assume that the rocket starts at the origin. So if we make that assumption, its initial position x0 is equal to 0. Okay, it does say in the problem that the rocket starts from rest, so then therefore its initial velocity v0 is equal to 0. Okay, and then the rocket undergoes its constant acceleration a in this direction. That acceleration is 9.8 meters per second squared. Incidentally, by the way, some of you may recognize that number of 9.8 meters per second squared. If you have done so, it's because it's a very well-known number. It's actually acceleration due to gravity. That is, if I take an object like so, and I release it from rest, it accelerates downwards at 9.8 meters per second squared. We'll get to the importance of that number a little bit later on in this unit. For now, however, the rocket's acceleration is given to us as that value. Notice that I didn't bother to write down a number line associated with this vector. Just writing down the vector itself, just drawing the vector is perfectly fine. Okay, and then we still know one more thing about the rocket, and that's at the end of the problem. We know that its final velocity, when it's over here, v, is equal to 1/10 the speed of light, which is 3 times 10 to the 7th meters per second. So those are all of the known quantities. And then the next thing that we do is we write down the unknowns. In the first portion of the problem, what we're asked to calculate is the amount of time necessary for the rocket to accelerate up to this speed. So then therefore the time t is unknown. Later on in parts C and D of the problem, we're also going to be asked to calculate the distance that is traveled by the rocket. The distance that is traveled by the rocket is the magnitude of the final position vector, x, like so, with respect to the origin. So now I've written down the unknown quantities. So this right here is the first couple of steps of the method, and now we start to get to the math. Okay, the first step of the math is to write down the relevant equations. This is one-dimensional motion with constant acceleration, so then therefore the following equations apply to the problem. So here's position as a function of time, and then secondly, here's velocity as a function of time. And now we start to simplify those equations by plugging in our zeros. Let's do so first of all with the velocity equation. Over here in the velocity equation, the initial velocity of the rocket v0 is equal to 0, because recall that the rocket begins at rest. So let's immediately simplify that expression such that it becomes the following. This expression here. And now if you look at the expression carefully, you should notice that only one thing is unknown, and that's the time t, so then therefore we can algebraically solve for it. So to solve for the time t, I'm just going to divide the acceleration a to the other side, such that then therefore the expression ends up being the following. And now I can go ahead and plug in my numbers. So in the numerator of the expression, we have the final velocity of the rocket, 3 times 10 to the 7th meters per second. And then in the denominator of the expression, we have its acceleration, which is 9.8 meters per second squared. Okay, I'm going to go ahead and do the math first of all here on my calculator. I'll round it off a little bit. That's perfectly fine. And now I have, first of all, 3 times 10 to the 7th in the numerator, and then divided by 9.8. And that comes out to be about 3.06 or so times 10 to the 6th. And then here's how the units work. Take a look at the units in the following portion of the problem. The meters here in the numerator cancels with the meters here in the denominator like so. And then a second cancels here and here like so. And then in terms of the units, what we're left with is 1 over seconds, which is just in terms of seconds. So we end up here with a time in terms of seconds, as we should. What you saw me do here with the units, by the way, is a little bit of what is called dimensional analysis. Dimensional analysis is working your way through the units in your algebraic expression to arrive at the units that you should be calculating, in this case a time in seconds. Now even though this problem here algebraically is rather straightforward and easy, every now and then you may encounter a problem that's a little bit more difficult algebraically. So one way that which you can check yourself when you get to the end portion of the process here is to check the units. Do a little bit of dimensional analysis as I did here and see if the units work out as they should. If they don't, then you may have made an algebraic mistake earlier in your mathematical manipulation. Okay, now this is the time here that we've calculated in terms of seconds. 3.06 times 10 to the 6 seconds, that's 3.06 million seconds. That's a lot of time. So then therefore in part B of the problem now, it asks us to convert this time in seconds into days. That will give us a better understanding as to exactly how large this number is. So this right here was part A of the problem. Now let's go ahead and take a look at part B. Okay, so I have this time here of 3.06 times 10 to the 6th seconds, and now I'm going to go ahead and convert this into days. I'll do so by doing a series of steps. So the first thing to do is convert the seconds into minutes. There are 60 seconds in a minute. So now I'm going to multiply by 1 minute per 60 seconds, and notice that the seconds cancels like so, and now I'm going to have a time in minutes. Let's then go ahead and convert this time in minutes to hours. There are 60 minutes in an hour. So then therefore the next thing to do is multiply by 1 hour per 60 minutes. The minutes cancels like so. And then lastly, we'll go ahead and convert the hours here into days. There are 24 hours in a day. So now multiply by 1 day per 24 hours. Notice now that the hours cancels like so, and then I'm left with a time in days. So basically what I have to do here is take 3.06 times 10 to the 6th and then divide it by 60, divided by 60, and then divided by 24. So going through that process here in my calculator yields a time in days of about 35.4 days. Like so, which is just over a month. So then therefore, if you take an object, for example, like so, and let it continuously accelerate at 9.8 meters per second squared, not for a split second here at my desk, but for 35.4 days, it will actually reach a speed of 1/10 the speed of light. Okay, now in parts C and D of the problem, we're going to calculate how far the rocket travels when it undergoes this acceleration. As you'll see, it's going to be quite a large distance. So now for part C, let's take a look at the position equation. So once again up here on the top board, this is describing the position as a function of time. Let's now go ahead and simplify this equation by plugging in our zeros. So first of all, we have x naught, which is equal to 0. Remember that we're assuming that the rocket begins at the origin. V naught is equal to 0 because once again the rocket begins at rest. So these two terms here are equal to 0, and then therefore the equation for x simplifies to become the following. Like so. And now I once again plug in my numbers. Let me write them out for us here. So I'm going to take 1/2 times the acceleration of 9.8 meters per second squared, and then I multiply by the time in terms of seconds squared. So then therefore I have 3.06 times 10 to the 6th seconds quantity squared, like so. So I plug in the time in terms of what are called the base units of seconds, not in terms of days. If I accidentally plug in the time in terms of days, then the units will not work out as they should. So let's go ahead and take a look and see exactly how the units are going to work out here in this portion of the problem. So what I have here is seconds squared, and then notice that that's going to cancel with the seconds squared that I have right here, like so, and then therefore I'm ultimately going to end up with a position, the distance traveled by the rocket here, in terms of meters. So now let me go ahead and work my way through the math here on my calculator. So I take 1/2 times 9.8, and then times 3.06 times 10 to the 6th squared. So I'm just squaring this guy right here, and I end up with quite a large distance, as you might imagine. So ultimately, this then works out to be, let me make sure I do the math here correctly, 1/2 times 9.8 times 3.06 times 10 to the 6th squared, there we go. So if I do the math correctly here, it works out to be about 4.6 times 10 to the 13th meters. That's 46 trillion meters. That's 46 billion kilometers. That's quite a large distance. So to give you an idea as to exactly how big this distance is, lastly in the problem it asks us to convert this value into astronomical units. Recall from the first unit of the course that an astronomical unit is the distance from the Earth to the Sun. That is by definition 1 AU. So how many AUs is this equal to? Well, 1 AU is about 150 million kilometers. That's 1.5 times 10 to the 11th meters. So now let me go ahead and convert this value from meters into AU by using that conversion factor. So this is part D, the last portion of the problem. So I now have 4.6 times 10 to the 13th meters. And now I multiply by 1 AU per 1.5 times 10 to the 11th meters. Once again, 1.5 times 10 to the 11th meters is 150 million kilometers. And that's the distance from the Earth to the Sun. So now the meters cancels here, and then I'll be left with a distance in terms of AU. So let me go ahead now and just divide out by 1.5 times 10 to the 11th meters, like so. And I end up with a distance, I'll round it off a little bit, of about 306 AU. To give me an idea as to how large this distance is, the average distance that Pluto is from the Sun is about 40 AU. This is nearly 8 times that value. So then therefore, if I take this paperclip, for example, and I release it from rest like so, such that it accelerates at 9.8 meters per second squared continuously for 35.4 days, it will reach a speed of 1/10 the speed of light, and it will travel a distance that is nearly 8 times the distance that Pluto is from the Sun. So right off the bat here in this course, yes, we are doing a little bit of rocket science. Okay, let me go ahead and pause the lecture here for this portion of the lecture.